So this is part 8 of our introduction to pseudospectral methods. And in the previous presentation, we presented some examples of using Chebyshev pseudospectral methods in one dimension. So here we're going to extend that to 2 dimensions by first looking at the 2D transforms on the roots grid. So here we can see the inverse transform and the discrete transform here. And the term in brackets is a one-dimensional transform for each of these. So the 2D is simply a one-dimensional transform nested within a two-dimensional transform. So if we look at the discrete cosine transform, we effectively, for each value of x, we do a discrete cosine transform over y lines, that is, over the k indices. And we're effectively sweeping the discrete cosine transform over y lines as we do that for each x location. This gives us, in this term in brackets, a matrix A tilde Jm, where the tilde is for almost there, where we've converted, we want A indexed by wave numbers with indexes n and m, but so far we've only done the m portion, so we're indicating this tilde just to note that we've only partially completed. And then once we compute these, we sweep over x lines for each m value to get to convert the x into n. And similarly for the inverse transform. So this is for the roots grid. For the extrema grid, it's shown here and is similar. So let's code these up. So we have a discrete cosine transform in 2D and an inverse discrete cosine transform in 2D. And here we're making use of one-dimensional discrete cosine transforms. We basically have a loop over nx and then a loop over ny. Doing the first part, this will create the tilde, and then once we're done with the second loop, we'll have the transformed quantity A. And we do something very similar for the inverse transform. These give results identical to the DCTN and IDCTN discrete cosine transform in where n represents an arbitrary number of dimensions. So we can see that by creating an array, just a random array of size 4 by 3, and we compare this discrete cosine transform 2D to the discrete cosine transform operating on A. We get the same result. The number of dimensions, this function DCTN infers the number of dimensions from the shape of A, so you don't have to explicitly tell it the shape. Here I've got type equals type, where I'm saying whether we're on the roots grid or on the extrema grid. Okay, so pretty straightforward to do these 2D transforms. The derivatives, in order to compute derivatives on the 2D grid, I'm showing a derivative with respect to x. And in this case, it's basically just like it was for the Fourier, discrete Fourier transforms in 2D, where we can consider a line of points and just compute the derivative along that line. So duk dx would be the array of u values at all the j in the x direction at a given single k direction, and we can just use this. This is basically the same as it was in 1D. So we just consider, if we're doing du dx, we just consider all the points along x for a given y. And similarly, if it's du dy, we look at all of the points in in y at a given xj. So pretty straightforward to do those 2D derivatives. So let's look at the two-dimensional heat equation that's shown here. No source term here. And we'll just let the diffusivity gamma equal 1. And then I'm using a domain size of 2 in both x and y that varies from -1 to 1 as usual. And then Dirichlet boundary conditions with a unity initial condition in the center, center block square portion of the domain. Okay, we'll solve this using both pseudospectral and the finite difference method. So we set our grid, and then our grids will be a little different if we're using a finite difference method. I'm going to use a uniform grid, and if we're doing a finite or the pseudospectral method, I'll use the Chebyshev grids. And then set the initial condition to be the block, and then we define the rates here for the Chebyshev in 2D and the rates for a finite difference method. And so for the rates, we initialize the derivative with respect to x and y, second derivative. And then to compute these, we're going to we're going to sweep over, so here we're computing the derivative with respect to x. Here we're computing the derivative with respect to y. So when we're doing x, we're going to sweep all over. We're going to sweep the y positions and then compute the full line of second derivatives in the x direction using this same equation right here. So first we take a discrete cosine transform, scale it, take the derivative, unscale it, take the inverse. So we take the cosine transform, then we let's see, what do we got here? Sorry. So we have the cosine transform, then we take the derivative of it, then we scale it, and then we unscale it. Sorry, we have these, the scaling is done here. So discrete cosine transform, then we scale it, then we take the derivative with the appending, then we unscale it, so times a half, then times 2, and then we take the inverse transform. Okay. And then we do something similar in the y direction, and then form the final rates, and then we can advance this using ODE int. And the finite difference method is just a simple second order central difference. Okay, so let's see how it does. And this doesn't have a source term, so, and it's got Dirichlet boundary conditions that are 0, so this profile is just going to diffuse away towards 0, uniformly 0 profile. And we get basically the same thing when we do the finite difference, at least visually. Okay, so that is the presentation of these pseudospectral methods, and I'll just give a couple of notes on these. So we've been using, we've been applying this to an unsteady PDE that has a temporal term, and so this is convenient for solution with the method of lines. If we use explicit solvers, then the stable time step tau for advection terms, a first derivative would be tau goes as the grid size delta x. So for instance, if we have advection, the time scale would be delta x over the advective speed, and if the advective speed is constant, it goes like delta x. For diffusive terms, second derivatives, the time scale goes like delta x squared over the diffusivity. So for constant diffusivity, it goes like delta x squared. Fourier pseudospectral methods use a uniform grid, and that means that delta x goes like inverse of n. So if we double the number of grid points, we half the grid spacing, and that means that tau is going to go like 1 over n for advection, and tau will go like 1 over n squared for diffusion. So if you double the number of grid points, you have to take 1/4 as big of a time step size. Now, for Chebyshev interpolation, we use a non-uniform grid. And in that case, our grid spacing, delta x, looks like 1 minus cosine of pi over n for n plus 1 grid points. And if you look at this, the first two terms of the Taylor series expansion of cosine x are 1 minus x squared over 2. And this means that when you plug this in for this cosine term here, delta x goes like 1 over n squared, and tau goes like 1 over n squared for advection, but for diffusion it goes like 1 over n to the 4th for diffusion. So that's painful, because as you increase the number of grid points, your required time step size decreases by to the 4th power. That's a big constraint and a major limitation of the method. It's workable. You can work through it. Boyd, in his book, Fourier and Chebyshev, Spectral Methods, discusses using implicit or semi-implicit approaches to get past this. Again, just to highlight that, let's just look up here at our grid. So when we project, the idea is when you add points, you get a finer and finer cluster near the boundary. Now, it's possible that the number of points you have due to the grid gives a finer spacing than what is needed to accurately resolve the profiles. And in that case, you can use a semi-implicit or implicit method to avoid the time step change, provided that you take time steps that are sufficiently small for accuracy, given the resolution of the structures on the grid. So you have to be careful, because implicit methods can let you can bite you if you're not careful. Just because it's stable doesn't mean it's accurate. So you have to be careful about that. However, in pseudospectral methods, the Fourier or Chebyshev basis functions are used to evaluate the derivatives accurately. From that perspective, it's not necessarily so important whether the domain has periodic or non-periodic boundary conditions. So, for example, a uniform grid could be used on a problem with Dirichlet boundaries and derivatives computed using a Fourier basis if the domain was mirrored so as to make a continuous periodic profile that would be appropriate for a Fourier basis. So, and then accurate derivatives could then be used to advance a time-dependent problem. So the idea is you might have a non-periodic problem, but you can make it periodic if you just mirror the profile and put one next to the other. And then you could apply a uniform grid with a Fourier basis to compute the derivatives. So that could be considered. You can also consider cases like a vertical jet, for example, in a free stream with non-periodic far side boundary conditions. It doesn't really matter that they're non-periodic if the profiles approach 0, for example, or some constant in the far stream, and that constant is the same on all sides of the domain, then it doesn't really matter that the problem is periodic or not. You can apply Fourier modes using, for example, a uniform grid to compute accurate derivatives, at least in certain regions, and then modify those derivatives as needed for Neumann or Robin conditions, for instance. A Chebyshev pseudospectral method would use a grid for that same problem, like a vertical free jet. A Chebyshev pseudospectral method would use a grid with the highest clustering of points near the free stream boundaries where nothing is happening. So that's not great. And in contrast, like pipe flows, most of the action happens near the walls, and so a finer clustering near the walls makes a lot of sense. Also, we haven't said anything about spectral element methods, but you could think of these Chebyshev pseudospectral methods as a prerequisite for looking at spectral elements, where rather than considering global functions across the whole domain, you would consider localized regions that you apply higher order methods to. And that can be convenient for application of domain decomposition problems, or where you're parallelizing the domain, for example. So this has been the full introduction, and I hope these notes are helpful to you. Please let me know if you have questions or edits and corrections. Thanks.